You've learned in Math 140, when you took that wonderful class that I'm sure everybody loved, about the unit circle. But you've also seen the relationship between the radius, for the case of a circle, radius r, arc length, let's call it s, and angle, let's call it theta. And you've learned the relationship between those two. The relationship that you've learned was that s, the arc length, was equal to the radius times the angle. In order for this to be true, make sure that you realize that since s is a distance in meter, r is a distance in meter, theta must have no units, which means that starting from now, you need to switch your calculator to radian. Radian is the same as no units. Degree is a particular unit. So make sure that if you're going to use this formula, you switch everything to radian. Since we're doing calculus, the beauty that we can do is we can approximate s to very, very small, which implies that we can consider and approximate s as a straight line, very small one. Therefore, we can define it as our usual displacement. That's the beauty of calculus. We're just going to take the limit for s being very small, and therefore we can consider it as our regular displacement x. Let's do a little bit of, therefore I'm going to be able to rewrite this as x is equal to r theta. And now let's apply a little bit of calculus. Let's apply the derivative to this equation from the left side to the whole equation. Let's apply it to the left-hand side, and do the same thing on the right-hand side. This will give us dx dt is equal to dt of r theta. So far, so good. Why are we doing this? Because look, what's showing up on the left-hand side? Here's something that we have seen before. And if so, could you refresh my memory or everybody's memory on what this is? dx dt from chapter 2. Yeah, linear velocity, excellent. So this is nothing else but the linear velocity. So already linear velocity is the first derivative with respect to time of the product of r, which is the radius of a circle, and the angular displacement theta. Mathematically, we need to be careful here. We have a product, therefore we need to use the usual product rule. So let's hold the first one constant, r, and let's apply the derivative to the second term. And then let's hold the second term constant, and let's apply the derivative to the first term. So far, so good, basic calculus 1. Since we're dealing with a circle, the nice thing about a circle versus an ellipse, which we will see in chapter 13, which make life a little bit more complicated, is that r is invariant. So if the radius of a circle is invariant, its first derivative with respect to time is naturally 0. Ping! And the second term goes away. Therefore, we have v is equal to r d theta dt. V is the linear displacement, r is the radius, and d theta dt is going to be associated with what we call the angular velocity. So we have discovered two new concepts. Theta, this is the angular displacement. Technically it should be delta theta, but doesn't matter. That's the cousin of linear displacement, x. Then we had known and recalled v, linear velocity. And we've just seen that there is not only a relationship between linear displacement and angular displacement, which is x is equal to r theta. But now we just discovered a similar relationship between the linear velocity and the angular velocity. And by doing so, we have introduced a new concept, omega, which is going to be the angular velocity. Just by applying a nice, easy transformation. Good. We know that the units of velocity is meters per second. The units of r is meters. Therefore, the units of omega must be 1/second. Or radian per second. While theta is in radian. Or no units. All right, let's keep going. Let's apply the first derivative with respect to time of the velocity equation. We're going to do the exact same thing, apply the chain rule, the product rule, and we will end up with dv dt, which is linear acceleration, is equal to r times d omega dt, which is defined as alpha. Linear acceleration was a. We've just introduced its cousin, alpha, angular acceleration, by using the exact same relationship. And sure enough, its units will be 1/second squared for the units to hold true. So as we can see, the kinematic variables that you've learned in linear motion can be the same in angular motion. This alpha is the one that allows us to go faster and faster in a circle. That's the tangential acceleration, which is different from the radial acceleration that we've seen, which was towards the center. So this alpha is the one that allows us to go faster around that particular circle. That's the one we have not considered so far. Now we're going to consider it. Okay? If you read the book, and I strongly suggest that you do, they have done a good job. I remember when I reviewed that chapter, I reviewed this chapter, chapter 10 and chapter 30 on quantum mechanics. This one was pretty good, but they were missing the vector relationship. And so they included it. So if you're going to be ME and you're going to plan, or C, and you're planning to take C271, please read the book and look at the derivation in vector form. This will help you a lot in C271. If you're EE, don't worry about it. Just stick with the scalar relationship. In this class, we are only going to use the scalar relationship. But again, if you'd like to go ahead and be prepared for 271, which is quite a toughy class, make sure you look at the section, chapter 10, to look at the vector relationship. The book has made changes and they did a really good job. What's important, and all I want to point out, is if there is a vector relationship between those three guys, if R is here, and I'm going in counterclockwise, linear velocity is tangential, as usual. If there is a relationship between those, R, omega, and V, in the vector form, what do you think omega direction must be? No guess? This is the vector notation. Excellent, Tim. Excellent. It gotta be perpendicular to the board, which is a little bit weird. But all those kinematic variables in rotational, alpha, omega, and theta are all perpendicular to the board. Even though in most books, they show it like this. Very misleading. So remember, W is either into the board or out of the board. But again, let's leave this on the side because we haven't seen this particular bugger, but we will do this in 15 minutes. But as we are going to investigate the cross product, please revisit this concept on the book and see how they derive it using vector notation if you're going to be CNME. Okay, so obviously we have discovered new relationship between all the linear kinematic variable x, v, and a, and the angular kinematic variable theta, omega, and alpha. And the relationship that we discovered for all of them is just a stupid R. So if you remember one, you will remember all of them. Make sure you do. That's going to be very important. This is suggesting that all the equation of motion that we've derived in chapter 2 and chapter 4 can be applied here. Let's take the first one. X is equal to x naught plus v naught t plus 1/2 at squared. Let's substitute all those relationships. Theta r is equal to theta r naught plus, I'm sorry, not theta, r omega naught plus 1/2. A is going to be r alpha t prime. R shows up in every term. And now we have angular displacement theta is equal to the initial angular displacement plus the initial angular velocity times time plus 1/2 angular acceleration times t squared. Exact same equation of motion as chapter 2 and chapter 4, whether you do linear or angular. That's a beauty, which means that all the type of problem we've done in chapter 2 and 4 can be done in angular direction as well. All we have to do is every time we see a x, we put a theta. Every time we see a v, we put a omega. Every time we see a, we put an alpha. Okay? So we've done problems and we went over chapter 2. I'm not going to waste your time by doing stupid problems such as let's start from rest and let's go in a circle for 2 seconds with an angular acceleration of 3 radian per second squared. What is my final angular velocity? If you know how to do chapter 2, you know how to do this one. All you have to do is add the angular term in front of every term, and it's the exact same problem. So instead, I will focus on one particular application of the relationship between linear kinematic variables and angular kinematic variables, which are gears. And this will be useful for CE and ME. If you have gears, one gear in contact with another gear, let's imagine that their radius is the same. Let's imagine that they have teeth, you know, like a gear. So a real gear would be like this. Like that. Such that as gear A is in contact with the gear B, there is no slipping. We're always going to have the same condition as when we did Atwood with pulleys. If gear B is rotating clockwise and there is no slipping and is doing it with a particular angular velocity, what do you think, if you ever watch gears connected together, what will be the direction of the rotation of gear A? Is it also going to be clockwise, or is it going to be opposite? Excellent. Counterclockwise. So the direction changes when two gears are in contact. But now, let's imagine that you put a mark on here. Obviously, this point is going to have a linear velocity. And if you rotate this gear by a particular angle theta, obviously the other gear is going to rotate by the same amount. Since they are in contact, every time you're going to have a contact with no slipping, you will be able to assume that at contact, the linear velocity is the same. That's the beauty of gear. At contact, if there is no slipping, the linear velocity of any point on the rim of that gear is going to be the same. So, if you apply the relationship between linear velocity and angular velocity of both gears, we therefore have VA is equal to R omega A. And similarly, VB is equal to R omega B. If those two gears are in contact and there is no slipping, the linear velocity will be the same. Therefore, R omega A is equal to R omega B. And in this case, the angular velocity will also be the same. So far, so good. The only difference is we have to be careful. Those are scalar relationship. So it doesn't take into account the change of direction. But now if we consider gears with different radius, if this one rotates with a particular angular velocity omega A, big R, small r. If you've seen gears rotating in contact with each other, do you think the small gear, or if you ever watched such a dance, was the gear B rotating faster or smaller? If you set the angular velocity of the big gear and you watch the velocity of the small gear, if you had that experience. Anybody has been playing with gears? Or Lego that had gears? Yeah, I thought it was only the French who had gears in Lego. Yeah, excellent. So we know intuitively that the angular velocity of the small gear will be bigger. Well, let's verify this. Again, if we consider the condition that there is contact and there is no slipping, the linear velocities are the same. But now the difference is they all have their own radius. So let's keep track of that. As we equate the two, we now have omega A is equal to RB divided by RA times omega B. So if we set omega A, I should have solved for omega B. Therefore, omega B is equal to RA over RB omega A. So if we set omega A to a particular value and RA is bigger than RB, then obviously RA over RB is bigger than 1. Therefore, omega B is bigger than omega A. Okay? So this is a nice condition that is very, very, very useful in all types of engineering, especially CNME, where you can change the angular velocity between gears. This is exactly how your gear shift works. If you have a manual, if you have a car and a manual stick, that's what you do. When you press the, what is the name of that pedal? The one on the left to release the little, thank you, John. If you press the clutch on the left, what you do is you separate the gears. As you switch gear with the stick, you translate those gears in or out of the board. So if you look at those gears from the top, you will have two shafts and you will have different gear radius. So as you do the clutch, you separate them. As you change gear, you translate one of them. And so therefore you put in contact different ratio of gears. That's how you switch gears in a regular car. I mean, manual car. And that's what the automatic does too, but it just do it by itself. So just with this concept, basic notion of kinematics, linear, basic concept of kinematics, angular, you can analyze a whole clutch by yourself. I remember that was one of my test in high school diploma. They just give me a gear shift box full of oil, and I had to figure out how that works with just this relationship. Very simple. So quite powerful. So that's the only application that I would expect you to be able to reproduce in tests with respect to the relationship between linear velocity, angular velocity, linear acceleration, angular acceleration. The relationship holds the same. It's the linear component that is the same if we consider contact and no slipping. But let's try to get a better feel about the difference between V and omega. If you are on a merry-go-round, the merry-go-round is rotating, say that way. Let's say there is a little kid right here at a distance of R1 and another kid on the rim, distance R2. Both kids are mounted on the merry-go-round platform. If they're, well, mounted, quote unquote, they're not moving with respect to the platform. And the platform is moving with a particular angular velocity. Since there is no relative motion between those two kids, they share the same angular velocity. We both agree that if the platform rotates by an angle theta, this little kid will end up being here. The angle theta is the same here. Therefore, that little kid will be here. So they both change their angular displacement by the same amount of time. So they both share the same angular displacement. Therefore, omega of little biped 2 is exactly the same as omega of the little kid 1. They're both the same. If they're both the same, do you think that their linear velocity will also be the same, or will it be different? And if it's different, which one is going to be the biggest? If now we make the R2 will be bigger, yeah. R2 will be bigger because R2 is further away from the center. Therefore, for the same amount of time, R2 will have to go through this distance, which is much bigger than that distance. And those are x. Excellent, John. Thank you. So in this case, V1 over R1 is equal to V2 over R2. And in this case, if we solve for V2, we end up with R2 divided by R1 times V1. Again, if R2 is bigger than R1, R2 of R1 is bigger than 1, therefore V2 obviously is bigger than V1. Okay, so that's for merry-go-round type of system. It will change as we do chapter 13, orbital dynamics, because we're not, all the planets are not stuck on one sheet of ether that some other dudes figure out doesn't exist. Okay, so when you go in a circle on a merry-go-round type of situation, therefore there is no relative motion between all the systems that go around. They share the same angular velocity. The further away from the center are the ones who will have the higher linear velocity, because the distance from the center is the further or the highest. Okay. What about if we have two gears that are not connected by a belt, which every car has? This is exactly the same as contact. The relationship is the same. If there is no slipping here, no slipping here, every point that has a particular linear velocity here will have exactly the same linear velocity there. So the belt is the one that relates the same contact as before. The only difference between this system A and this system B is that the direction will be the same. So if the angular rotation of R2 is clockwise, then the rotation of R1 will also be clockwise. While if they're in contact, we've seen earlier that they have the opposite direction. That's all. But otherwise, the contact, no slipping condition applies exactly the same way. So now that's cool, because if you have a belt on the rim and you have another rim, so if you look at this from the side, it's a disc with an inner disc, and you attach the belt right here, you still have the same condition. V1 is equal to V2. But this R is going to be different from this R. And hence, you're going to be able to relate the angular velocity. And then if now you connect this with another gear, this had omega 1, this have omega 2. Obviously, you know that omega 1 is different from omega 2. Obviously, in this case, omega 1 will be bigger than omega 2. As you try to relate this disk with this disk, what is the relationship between point A and point B? They share the same angular velocity. Therefore, omega 2 of B will be the same as omega 2 of A. And then you can reconnect this by point C. Once you get omega 2 of A, then you can deduce V2 of A. And this one is the one that will be common to V2 of C. So you can connect n number of putties with, different belts, look at a different size with respect, different position with respect to the center, and be able to change the quote-unquote gear ratio between all those. And you can add as many as you want. Beautiful thing. Gears are a beautiful thing. Okay. Let's go back to now. We've reviewed kinematics in rotational dynamics. We've investigated the angular acceleration that we neglected before. We've only considered the radial acceleration, which was equal to v squared over r, and whose direction was towards the center. Alpha is the one that's tangential, therefore collinear to the tangential velocity. That's the new alpha that we just discovered. Now let's do the same thing, and let's go back one more level and try to identify what could be the cause of angular alpha. We know from Newton's second law that the cause of linear acceleration was a force. Naturally, we could ask ourselves, well, what creates alpha? To do so, all we have to do is apply what we call the cross product between a position vector r and the net force F. But before we do this, and we look at how it's being applied in physics, let's go back to chapter 2. You've seen dot product. So let's do a little parenthesis here, and let's revisit chapter 2. We know that if we have vector A and a vector B, we can add them, we can subscript them. We've learned how to dot them, and we've seen that the dot product was one particular type of multiplication for vectors. We've seen that if we dot to vector, we end up with a scalar. We've seen that if A is perpendicular to B, then the scalar is 0. And if A is parallel to B in the same direction, then C is max, positive. And if A is parallel to B, but in opposite direction, then it would be C max, but negative value. Those were the property of the dot product. Let's investigate the property of a cross product. A cross B. This is going to give us a vector. That's the first difference between dot and cross. Those are two different operators that mathematicians have created. They don't know why, but they know how. As scientists, we don't care about why, but we care about how. We've been able to apply the dot product and realize that it fit exactly our concept of work, which was perfect for physicists. Let's investigate and learn about another type of multiplication called the cross product, and we're going to see that this one can be applied to something else in physics. So it's a win-win situation. They do all the work, we get all the benefits. Property of the cross product. First of all, it's not a scalar, it's going to be a vector. Second of all, so C is the vector. Second of all, C is going to be perpendicular to A, and C is going to be perpendicular to B. So if you have two vectors A and B that are on the plane, C is out of the plane or into the plane, 50-50. That's the only condition that satisfies this. It gotta be perpendicular to the plane. But it could be towards us or it could be away from us. How are we gonna pick? That's where convention shows up. If you have a vector A here and B here, and you do a cross product, A cross B, imagine that you're sweeping A towards B. This will give you a vector C, and this vector C is going to be towards you. Think of it as a screw head. If you're unscrewing a screw, you're going counterclockwise. The screw is going towards you as the positive direction. So that's the one we're going to pick. That's the world convention. If you pick a coordinate system such that you have X and you have Y here, and you're doing A cross B, you're going in the counterclockwise direction, therefore the result is positive. So counterclockwise will give you positive vector. That's the world convention. That allows us to differentiate from one to the other. British are using the opposite. It doesn't matter, it's just a convention. The sign will be different, but that's it. Okay, so in this class, we're going to use the world convention. Therefore, counterclockwise, positive. All right. Another property. If A is perpendicular to B, then we have maximum magnitude for C. But if A is parallel to B, then we would have the minimum, which is a zero vector. So this is exactly opposite to the dot product. Dot product, if the two vectors were perpendicular, the dot product was zero. If they were parallel, it was maximum. Cross product is the opposite. Okay? Several ways of calculating the cross product. I'm going to start with the first one, which I strongly suggest not and never use. Why? Because A cross B is defined as vector C, which is also defined as AB sin alpha. Remember, the dot product was AB cosine alpha. The problem with this is we need to be careful because this is only true for the magnitude of the cross product. So first of all, it forces us to know the angle between both vector A and vector B, which is fine, but sometimes it's a little bit more work. Second, this result only gives us the magnitude, which means we still have to figure out the direction on top of it. Second method, express both vector in component notation. Let's imagine 2 and 3. B, let's imagine 1 and 4. Cross product, another method which is a little bit long, is we're going to do this. We're going to use the distributed rule, and if we want to calculate A cross B, we're going to take the first guy of A, cross it with the first guy of B. Then back to the first guy of A, cross it with the second guy of B. Then we're going to move to the second term of A, cross it with the first of B, and then second term of A, cross it with the second term of B. So just using the distributed rule. But let's keep our IAJ together. 2I plus 3J. I plus 4J. In this case, A cross B will give us 2I cross I plus 2I plus cross 4J plus 3J cross I plus 3J cross 4J. So far, so good. We can take all the scalars out and only look at the cross product of those vectors. 2, I cross I, plus 8, I cross J, plus 3, J cross I, plus 12, J cross J. All right, now remember what we said. A cross B is zero vector if A is perpendicular to B. Oh, I'm sorry, parallel to B. And the magnitude A cross B is vector A times the sine of the angle. Based on this, how can we use this condition? Do we see this somewhere? That is, can we use the first condition to calculate I cross I? What is the relationship between a vector I and itself? Are they naturally perpendicular to one another, or are they naturally parallel to one another and in the same direction? If you take a vector I and you duplicate that vector, another I, and you look at the relationship between those two I's, what is it? It sounds like a trick question, but it's really not. So if you have a vector I and you compare it with the same vector itself, are those two vector I perpendicular to one another? Are they parallel to one another? Which one of the two? Anybody in here? Yeah, they're parallel, right? Therefore, if they're parallel, what is the result of their cross product? Excellent. That's it. Zero vector. Zero vector. Remember, the dot product was opposite. It was only the like term, I dot I, that survived. I dot I was equal to 1. J dot J was equal to 1. I dot J was 0. And J dot I was 0. Here is the exact opposite. Now let's investigate I and J. Let's put our ing at the top of the screw again. If we're doing I cross J, we're going counterclockwise. What is the unit vector that is perpendicular to the board and towards us? Do you remember what the name was from chapter 2? Yeah. Bang. That's it. But now if we're doing J cross I, we're sweeping that way. Remember the screw head. If you're looking at your screw from the top and you're going clockwise, what's happening to your screw? Your screw is going in, therefore it's going into the board. That's the opposite of the convention of vector k. Therefore, this is negative k. Hence, the result of this would be 8k minus 3k. So the overall is 5k. Okay? So that sounds like a lot of work, but there is some mnemonic trick for this, which is put all those ijk together next to each other. If you go right, positive. If you go left, negative. That's it, as long as you don't skip any. That means I cross j gives you positive k. J cross k gives you positive I. K cross I gives you positive j. So as you go towards the right, the outcome is always positive. But if you go left, k cross j will give you negative I. J cross I will give you negative k. K cross j will give you negative I, etc., etc. That's one way. But again, even that second method sounds like a lot of work. So let's look at a third method. This is called the determinant. You've seen this in Math 103 if you've taken that class. If you have not, you will see it again in Math 310 or 307. Very easy concept. You're going to put your ijk on the first row of a matrix. Let's say if you calculate A cross B. A will go second because it's the first one. So you're going to put the component of A. For us, it was 2 and 3. So 2, 3, and then 0 because he has no K. Then you're going to put B, which was 1 and 4. All right, 1 and 4. and then 0. And what you're going to be doing is calculate the determinant, which is you're going to hold the I term, cross everything else, and look at this 2 by 2 matrix. And all you're going to do is take this one, multiply it by this one, turn around, add a negative sign, take this one, multiply by this one. So this will be I 3 times 0 minus 0 times 4. That's it. Okay? Then you're going to jump to the next one. J. As you focus on the next one, you're going to put a line across this, a line across this. Now you're going to consider this 2 by 2. But the word convention forces you to put a negative sign. And the source comes from linear algebra in general that you will learn in 310. But you use the same technique. This guy times this guy, turn around, minus this guy times this guy. So for us, 2 times 0 minus 0 times 1. Both are 0. 0i, 0j in this particular case. All right, let's go to the last one. Hopefully something is not 0. Seems like it's going to be the k. Circle the k, draw a line, perpendicular, horizontal, and use the same technique. This guy times this guy, turn around, minus this guy times this guy. Positive k. 2 times 4 minus 3 times 1. And this is 8 minus 3, 5. 5k. Same. The beauty of this method is now you can have a 3D vector, which will give you all the terms. While this stupid thing only works in 2D. Otherwise, you need to figure out all the cosine angles, which is the angle between the x, the y, and the z. So the determinant is superior to all other methods in the sense that it can be used in 2D, 3D, 4D, 5D, 100D. And the other beauty is this is in most of your calculator. The calculator that you should get right away if you have not. And that you need to get if you have not yet in order to survive either E211 or C270 or C271. They will be expecting you to have those. They will be expecting you to do this through your calculator. Because by hand it's going to take way too long, which means you're never going to finish any test. Usually it's called href or det or whatever. So all you have to do is enter your coordinate of each vector, find the little button, press the magic one, and boom! And again, naturally, it's going to give you all the terms. So k is expected because we've seen earlier that if a is 2 and 3, it's in the plane. B is 1 and 4, it's also in the plane. Then a cross b will be perpendicular to the plane. In this case, we're going counterclockwise, therefore we expect positive. Sure enough, it's positive. If we were going to do b cross a, we would get the exact same magnitude, 5, but into the plane. Therefore, negative 5k, which you can verify easily by switching a and b. So if you put 1 and 4 on the top and 2 and 3 on the bottom, you will end up with negative 5k. So everything is consistent with this convention. I is positive, j is negative, k is positive, regardless of the outcome of the fish technique. Okay? So please revisit chapter 2 and master this. Cross product, same thing as the determinant, is going to be very, very useful later on. So for us, it's perfect because that's what we need to do. We need to take the cross product between the position vector r and the force F. Therefore, all we need to do is calculate the determinant. And that's it. So, as you apply the cross product to Newton's second law, and I'm going to do it in magnitude as well. But if I recall, the book did it in vector rotation. you're going to have M, you multiply by R and A. So I squeeze R in between because M is a constant. But remember what A was with respect to alpha. A was R alpha. Therefore, M R R alpha. Which means that this weird bugger, R cross F, is M R squared alpha, where my little r was the same as my big R. This is what we're going to call the moment or the torque. So that's going to be the magnitude of the moment. This is telling us that every time you want to create an angular acceleration, you need to apply a torque. Physicists use torque, tau, engineer use moment, m, same thing. So this is how we're going to define R cross F. And in order to obtain the magnitude, we're going to define this as I. So the torque is also equal to I alpha. And this I is not called the inertia, like we used to call the mass in Newton's second law. This is going to be called the moment of inertia. Because this is a torque or a moment. That's how we differentiate one from the other. Okay? So in summary, when you do translation, you try to figure out what causes the linear acceleration. It's just a force. M is the inertia. If you set particular force, magnitude, and direction, you're going to create a linear acceleration. And the inertia, or the mass, is going to be the resistance to the acceleration. The bigger the inertia, the less the acceleration, and vice versa. Now and that's for translation. Now for rotation, same concept. We just take the cross product of Newton's second law and we end up with sum of the torque is equal to I alpha, which means that for a given torque, a torque will create an angular acceleration. And instead of dealing with inertia m, or mass, now we're dealing with the moment of inertia I, which depends not only on the mass, but how the mass is distributed. That's the element r. And again, the higher the moment inertia, the smaller the angular acceleration for a given torque. And this torque is nothing else but R cross F. That's our new concept. That's what we're going to focus on in the next 5 minutes. So, what does that conceptually mean? Take a screw again. Up, 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 screw head. And take a wrench. Up, oops, up, oops, bang. Torque is going to create an angular acceleration. In layman's term, it's going to create a rotation. But it needs to be accelerated. Same as Newton's first law and the difference between the second law. So let's use the late term and use rotation. This is the axis of rotation. That's the axis about which the screw and the wrench are going to rotate. This R is defined as a distance. It's not a radius. It's a distance between the axis of rotation and where this force is applied. So if you apply a force here, located at a distance R, are you going to create a rotation? And I'm banking on the fact that you've all used a wrench. If you haven't, hopefully you've seen movies and you know how this little particular thingy is operated. Excellent. Obviously, if you apply a force F in that direction, they ain't gonna rotate. Let's verify that this is consistent with the cross product. R cross F, we've been told that this create a torque, therefore a rotation. Look at the relationship between the R vector and the F vector. What is the exact relationship in words between the position vector? Yeah, parallel. Hey, what did we say? Parallel, 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 where are you, where are you? Bang. That's the property of the cross product. Bang. So this property fits exactly and reflects and predict exactly what we can observe. Excellent. Obviously, if you want to rotate, you need to give it an angle. And this now will tend to create a rotation which is counterclockwise. By how much will be the rotation? It will be by taking the product, remember, of, in magnitude, R cross, R times F times sine theta. So really, we're going to take R and we're going to multiply it by the component of F that is perpendicular to R. Because remember, we can always decompose vector F as F perpendicular to R plus F parallel to R. So R cross F can be written as R cross F perpendicular plus F parallel. As you use the distributive rule, R cross F perpendicular plus R cross F parallel will give you the torque. But we just saw that if the component of F is parallel to R, this is going to be 0. So really the only one that counts is F perpendicular. That's the one. But we can express F perpendicular from chapter 2, which is nothing else but F sine theta. And that's where this stupid definition comes from. R, F sine theta. Okay? So obviously, you agree upon the fact that the more we're going to increase theta, the bigger the torque. Because the sine is going to go from 0 all the way up to its maximum value, which is 1, which is occurring, hey, what happened to my, here, occurring when F is perpendicular to R. That's when we're going to get the maximum cross product. Again, this is consistent with, hey, maximum value is when they're perpendicular to one another. So everything is consistent with the cross product. It's wonderful. Okay? So obviously, if we change the direction between the force and the position vector, we can change the magnitude of the torque. You've all played with torques. You also know that if you change the position at which you apply that force here, is also going to influence the torque. Which is easiest, to apply that force F with your hand at a position far, far away from the axis rotation, position R? Or is it going to be easier if you apply your hand at a position closer to the screw? Which one is the easiest one? Further away or closer? For you to be able to unscrew the screw, let's say if it's gripped. Would you rather apply the force F close or further away? Obviously further away, right? If you ever burn a tire or broke a tire and try to change it, you have those little tools thingy, and I'm sure one of those tools is an extension. So if you cannot unscrew those stupid tire screw, put an extension, same amount of force, bang. That's based on the cross product. If you want to increase F, all you have to do is increase R without changing F. A beauty. And you want to make sure that R and F are perpendicular to one another. So to increase the moment or the torque, either you increase the position upon which you apply the force, and or you make sure that that force is perpendicular to R as much as possible. And in this case, they will call this the level arm. Okay? So that's the feel about what torque does. This, however, implies for us a bad news, which is we cannot represent our wrench as a zero-dimensional point and move the force at its center of mass. Can't do that no more. As soon as we start doing rotation, we have to consider the shape of our object and be very careful about where those forces are applied, because they will affect the magnitude of the torque. Okay? So, in 2D, you always have two options, the 2D method or the 3D method. Let's look at the 2D method. If you have the axial rotation, identify that A. Remember that the torque, by definition, is R cross F. R is the first one, F is the second. We've seen that the cross product doesn't commute. If you calculate F cross R, we're going to pick up a negative sign. No good. So if your axial rotation is at A, you've also seen that the position vector R starts at the axial rotation, that means A, and ends where the force is applied. So if the force is applied here, then R is starting at A and ends where F is applied. Make sure you write that down. 99% of the error with respect to torque is because people forget that definition. I'm so glad that I don't have much hair anymore, because if I had, I would pull everything out as I'm teaching C270. The whole course is R cross F. And still up to right now, people do not know what R is. That just drives me crazy. But if you do know the definition, life is super easy. So remember, when you calculate the torque, always specify about which point you calculate it. And then remember that this vector R, which is really the one you have to figure out, because F comes from Newton, you know how to do this, is the position vector that starts where you want to calculate the torque, about, which is usually the axial rotation, point A, all the way up to where the force is applied. And that's it. So, as we've seen earlier, we can decompose F as a component perpendicular and parallel to R. Parallel and perpendicular. And as we've seen, as we calculate R cross F, which is the same as R cross F parallel plus F perpendicular, the only one of those two terms that will survive is R cross F perpendicular, because R and F parallel by definition are parallel. If you know this angle alpha, then in this case, the magnitude of R cross F will be R F cosine alpha. So that's the reason why I mentioned that I don't like the definition of AB sine theta, because depending on what's given to you, you may need to use the cosine instead of the sine. So all you have to do instead of memorizing the stupid definition is just draw it, and life is easy. But this only gives you the magnitude. Then you have to identify the direction. In this case, if you put a pin perpendicular to the board at A and you apply the force F at a bar that has a length R, obviously you will tend to rotate that way. That's counterclockwise, therefore positive K. Okay? Similarly, you could have kept F but decompose R such that it is parallel and perpendicular to F. That is, you could have decomposed this guy. This is R perpendicular, and this is R parallel. It's a free country, you can do whatever you want. Therefore, R cross F could be R perpendicular plus R parallel cross F. Same thing, distribute both terms, R perpendicular cross F plus R parallel cross F. But similarly, R parallel is by definition parallel to F, so 0. Now let's look at what R perpendicular is with respect to geometry. If theta is here, then theta is here. Therefore, our perpendicular is r cosine alpha times f in the k direction again. So as you can see, whether you decompose f parallel or perpendicular to r, or decompose r parallel or perpendicular to f, ends up being exactly the same thing. The only difference is the cosine was married to the f, while now the cosine is married to the r. But sure enough, it doesn't matter which method you use. Okay? This could be a little tricky method. So if you decide to use a method, be very careful. That's usually the method where most people make mistakes. And the problem with this method is it only works in 2D. We want to go and be ready for 3D. So here's the second method. Let's go back to R, and we had F that was here. All you have to do is pick a coordinate system and center it at the axis of rotation. And you go back to chapter 2, and you express R in component rotation and F in component rotation. Let's stay general and pick 3. Let's imagine R is 5, 1, and 0, and F is entirely in the Y, so let's pick 3, 0, 0. All you have to do, if you want to calculate the torque about point A of the force F, you just set up the matrix. I, J, K. First one that comes is R, 5, 1, 0. Second is F, 0, 3, 0. Bing, bam, boom, done. In 2D, as we've seen, the I component is going to be 0, because you end up doing 1 times 0 minus 0 times 3. Similarly, the negative J component will disappear as well, because you end up doing 5 times 0 minus 0 times 0. As expected, the only one that will survive is K. That will give you 5 times 3 minus 0 times 1. Bang, 15K, done. Okay? And again, the beauty of this is now we could have guessed that K was into the board or out of the board because our 2 vector RF was on the board. But the advantage of this is now you can have an R vector towards you and a vector in whatever weird direction. And this method will give you the acceleration or the rotation along each of those axes, I, J, and K, at the same time, without you having to visualize anything. So it's philosophy method. Cannot be easier. That's the beauty of mathematics. In this case, it can be used to describe a physical concept entirely. Cross product, it's the same as moment. Done. Easy. Cannot be easier than this. Direct relationship. Oh, TJ. I'm sorry, I just realized you are Thomas. I'm sorry, I thought I had a TJ from previous semesters. I was like, what is he doing here? Is he bored or something? Sorry. It just popped up. Anyway, so, see? Determinant is going to save your life if you're CNME. So if I would suggest, to be safe, since you always have infinite of time in your test, set up the matrix. And if you're planning on taking C270, C271, that's going to be the only method that will save your life in those two classes. So you might as well learn right now. If you like the challenge and the trickiness and your EE, feel free to master and learn the 2D method as well. My suggestion is try both methods and identify the one you like best. And once you do so, stick with it. Okay? Any questions on torque, matrices, and determinant in general? Before we take a quick break and then we start applying all this carefully. Correct. We cannot change the order. That is, R cross F is not equal to F cross R. Absolutely. However, the relationship is clear. It's just a negative sign. So if you decide to use the opposite, F cross R, then just don't forget to multiply every one of your results by a negative sign. That's what British people do. The rest of the world decided to go the other way around. So I would suggest use the word convention. Make sure you use R cross F. Be careful of your calculus 4 book or 3, I forget. I don't know where you see moment in calculus. I think it's maybe 3. They tend to use the RF sign version. Same as you do dot product and they do application, they tend to forget the dot product for some weird reason. Okay, what else? So yes, excellent point. The dot product do commute. A dot B is the same as B dot A, but the cross doesn't. Similarly, the cross product is a vector. The dot product is a scalar. The dot product is 0 if the two vectors are perpendicular to one another, while the cross product is maximum if the two vectors are perpendicular to one another. And the dot product is 0 if the two vectors are perpendicular to one another. Oh, wait, what did I say? Hang on, let me try again. The dot product is 0 if the two vectors are perpendicular, but the cross product is 0 vector if the two vectors are parallel to one another. And the dot product is maximum if the two vectors are parallel to one another in the same direction, and is minimum or 0 for a cross product if they're parallel to one another. I think I got it right. Okay, so usually they're opposite to one another. So if you find this confusing, just memorize one, the dot product, you already know it, and just inverse everything for the cross product. The only difference is, remember, the new property of the cross doesn't have, the dot doesn't have with respect to the cross, is the cross product is not only a vector, but the vector answer is perpendicular to both vector A and B. Or in physics, the torque is perpendicular to R and perpendicular to F. That is, it behaves exactly as theta, omega, and alpha. It's perpendicular to the board. Okay? A little bit weird, but from a vector point of view and a cross product point of view, it has to be. If F and R are on the plane, the torque is perpendicular to the plane. And if you go counterclockwise, it's towards you. And if you go clockwise, it's away from you. So you have two, we've seen the screw rule or the screw analogy. If you've been playing with screws since you're 3 or 4, stick with that. Otherwise, there is the IJK mnemonic. Or next semester, you're going to see a third way to remember those stupid signs, which is the right-hand rule. So if you're familiar with the NM and you've taken electrodynamics or electrostatics, electrodynamics, which one of the two? I'm guessing electrodynamics. Yeah. They use similar things, similar trick with the right-hand rule. So you use your right hand and you play with 3 of your fingers and you assign blah blah to blah 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 to blah blah, and that works. I never understood that rule, but if that rule works for you, use that. Yeah, that's what I like. You know, I like screws. I'm a simple dude. Screws are simple. I always remember that if I go counterclockwise, the screw come out of the board, positive K, bang, boom, done. And if I screw the screw, I go clockwise, and therefore it's negative. That works for me. So identify which trick works for you, the screw, the right-hand rule, or the mnemonic IJK, 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 and then stick with it. Okay? Any questions before we apply this? Okay, so we have an hour and a half to apply this. We're going to make the most out of it, because this, again, is going to be the foundation for us to survive the other side of the equation. So right now, we're looking at the left-hand side of Newton's equation in this rotational form. Torque is equal to R cross F. And this is the part of the left side of the equation, which came from F is equal to ma. after we took the cross product with the position vector. So we need to focus on this, the left-hand side. We need to master the left-hand side, bing, bang, boom, bing, bang, boom, bing, bang, boom. The same way as we mastered in chapter 2, and we apply it to forces. We need to be able to add vectors, no problem. Whether you call those vectors acceleration, velocity, forces, momentum, doesn't matter. We need to be able to add them up. Same here. We're in the same stage. We need to be able to calculate cross product or bunch of moments or bunch of torques given any forces, because that's back to chapter 2 and determinant. Once we do this, then we can investigate what's happening on the right hand side. And the big difference between linear and rotational version is now we have to deal with a new guy, I, which is not just the mass, but the mass times r squared. Okay, so before we can handle the right hand side with alpha, the angular acceleration, we really need to master the left hand side. And that's pretty much 60% of C270. We only look at the Newton's first law, translation and rotation. That's it. But if you master it in this class, then C270 is a piece of cake. And then in 271, they put back the right hand side. And that's where complication occurred. They create a rotation. A torque creates an angular acceleration, the same way as a force was creating a linear acceleration. In layman's term, a torque creates a rotation. But remember, this rotation needs to be accelerated. If you're rotating at a constant velocity, it's still Newton's first law. Same as the relationship between constant acceleration or zero acceleration and the fact that the velocity is constant, but doesn't have to be zero. Same idea. So conceptually, a force creates a motion. That's the layman's term. To be precise, a force creates a linear acceleration. In layman's term, similarly, a torque creates a rotation. But in physics term, precise term, a torque creates an angular acceleration, which means if you have a torque acting on a system, if you consider whatever axis rotation, this system is going to go faster and faster as it goes in a circle. Because alpha is the one that makes it go faster and faster and faster. Remember, this alpha is not the one we talked about last 2 chapters. It's not the radial acceleration. It's not the one that causes the motion to be circular. This one is going to cause the rotation to be even faster, because alpha will create a change of angular velocity, the same way as A was creating a change of linear velocity. So all the concepts are exactly the same, except instead of thinking of terms of translation, now we have to think in terms of rotation.